Okay, so we have finished chapter 4 and we have gone through some of the problems at the end of the chapter. We'll start today with chapter 5. From chapter 5 now, we are going to start with the numerical methods. So this is now the end of the introduction stage that we were going through, and we are going to now start with the numerical methods that we are going to apply for different types of equations, different types of problems. The first thing that we have here now is the roots finding, and in this chapter we'll look at what we mean by roots problems, and we'll see how to use different methods to find the roots. Now, going back again to our example of the bungee jumper, it says that medical studies have found that when a bungee jumper falls, then there is a big risk that he's going to sustain a significant vertebrae injury. It means injury in the backbone. And this risk increases if the free fall velocity becomes more than 36 meters per second after 4 seconds of free fall. So when the bungee jumper is jumping and the velocity increases to 36 meters per second within 4 seconds of after jumping, then there's a big chance that this person is going to get an injury in the backbone. So suppose you are working in a bungee jumper company and your boss wants you to find the mass at which this criteria is going to be met, and he wants you to find it given that the drag coefficient is 0.25 kilograms per meter. Now we already found this from chapter 1 that the analytical solution for the velocity can be given by this equation. Velocity with time, of course, is given by this equation. Now, if we say that velocity is 36 meters per second after a time of 4 seconds, and we know the value of g and cd is given as 0.25, and we want to find from here the mass. So it says, try as you might, you cannot manipulate this equation to explicitly solve for m. When you say that you have an explicit equation, it means that you can take this variable on one side and find the other things. So let's say if you have an equation like z is equal to xy plus 3, and you want to find x from here, then you can rearrange the equation. You can say xy is z minus 3, then you can say x is equal to z minus 3 over y. So you can say now you have an explicit equation in x. It means you can isolate it, separate it, and bring the variable that you want to find on the left side, and you have the other things on the right hand side. So we call this an explicit equation. Opposed to that, we have what we call an implicit equation, in which you cannot separate out the variable and bring it to one side. So that, of course, needs some work to find the value of m, because you are not going to be able to separate it out and bring it on one side. One way of looking at the problem is that we subtract the velocity from both sides. So we say v minus V minus V on both sides. So here we will cancel and you'll be left with 0. So we can say that function of mass is this equation that we had minus the velocity, and of course we said it is equal to 0. Now we see that the answer to our problem is the value of the mass, which will make the function be equal to 0. This is what we call a roots problem, where you try to look for a value of a variable which makes your function be equal to 0. Okay, this is what we call a roots problem. If you go back to the quadratic equation, let's say you have ax square plus bx equal to minus c. Let's say I'll make it minus c. Now, to find the root, it means that you make your problem to be ax square plus bx plus c equal to 0. So you are saying that your function of x is equal to 0. When you solve this problem, you say that this is a roots finding problem, because you are trying to look for a value of x which is going to make the function become equal to 0. Roots problems, they occur when some function f can be written in terms of one or more independent variables, where the solution to the problem yields the solution to the problem. These problems often occur when a design problem presents an implicit equation. Now, implicit, we said that when you cannot separate it out on one side. Of course, if you can have an explicit equation, that's a straightforward solution, then you don't need to do anything there. Let's say you have the width given, let's say 3 meters. You want to find x, which will give us an area that's of 21 square meter. Now we know that 3x is 21, so you can directly put there, so you'll find x is 21 over 3, so you can straightforward find the value of x. That's an explicit equation, you can do it straightforward. When you get an implicit equation, then you need to see how you are going to find the value of this parameter of the variable. Some examples of root solving problems that we have in the engineering. Given a heat balance, let's say you want to find temperature. An independent variable, let's say, could be time and position, and parameters could be like the thermal properties of the material, the system geometry. Let's say, for example, that you have a room and you want to find the temperature after a given time, or you want to find that if the outside temperature, let's say, is 40 degrees Celsius and you want to maintain this as 22 degrees Celsius, then how much insulation you need here. So you need the thermal properties of the material you need to find. Or you want to know what's the thickness of the wall here, you need to find the system geometry. Or you want to find the temperature at different positions here, how much it will be. If it is 40 here, let's say, and you have an air conditioner here which is trying to maintain the temperature at 22. So these are what we call design problems. Or you could solve for a mass balance, let's say for a concentration in a reactor. Then your parameters would be the chemical behavior of the material. It's the rate kinetics that you need. The mass transfer properties, again the system geometry, the length and the width of the reactor or the radius of it. So in these different problems, you end up getting some design problems, which will end up again into a root solving problem. We look first at the graphical approach. It says use the graphical approach to determine the mass of the bungee jumper with a drag coefficient of 0.25 kilogram per meter to have a velocity of 36 meters per second after 4 seconds of the free fall. Let me copy this. I'll go to Excel. I closed Excel. Let me open MATLAB as well with it. Let's say only 3. And of course, we are going to need the equation for the bungee jumper as well. So we want to plot to find the value of the mass for the bungee jumper. Now let us decide on a range of values. So decide on a range of values. Let's say you have a bungee jumper, you want to find the mass. So this mass is of a person. So it needs a range of the mass that is suitable for the person. Of course, let's say we are not going to have a small child doing the bungee jumping, so you try to look for a range of a mass. Omar says from 50 to 160, Ali says from 40 to 150. Yeah, so we can try. Let's say we'll go from 40 to 200 kgs. Some of these people can go up to 200. So we'll plot here the mass and the function of mass. I have the mass. Let's say start from 40, and I'll say this is this. I take an increment value, 1 kg, 2 kg, whatever. Let's say 5 kg, so that I don't have to have so many values. And I need the equation now to put it here. So I'll say this is square root of g, which is let us define them, okay, before we write. G, CD, time, and velocity. So we said this is 9.81. We said this is 0.25. Time is 4 seconds. Velocity is 36. I'll give the name of G. I'll give this the name of CD. I'll call this time, and I'll call this velocity. So square root of G multiplied by mass divided by CD multiplied by hyperbolic tangent of square root of G multiplied by CD over the mass multiplied by the time minus the velocity. Yeah, don't forget that when we are writing the function of mass, we are taking velocity to this side to make it equal to 0. And we can copy this down, and we can copy both of them down to reach 200. Okay, let us stop at 200. I'll select both of them and I'll plot them. So this is quick plotting in Excel. So I have my plot in Excel. I have my mass values here on the x-axis, and this is the function value. The place where it crosses the 0, that is the root of our problem. That's the mass that is required. Okay, so that will be the maximum allowed mass. Let's say it seems around 140 kilogram. It's less than 150, so let's say 140. So that's the maximum allowable mass for the person, so that he does not have the risk of the injuries. Okay, so that's the graphical approach, how you can plot the function and find a quick solution. I'll go to MATLAB. Better always to work with a script file. I'll close this. I'll say new script here, new script, and I'll write here. Good idea always to start with the clear statement. Then I define my variables. I say G is 9.81, CD is 0.25, time is 4 seconds, and velocity is 36. I'll define a range for mass. I'll say mass is linearly spaced vector. You'll find this in chapter 2 or 3. And I have the intervals that I will give from 40 to 200. So that will create for me a vector of values for the mass from 40 to 200. Then I can give my equation for the function of mass, and I say it is square root of gm over cd, m over cd, yeah, multiplied by hyperbolic tangent of the square root of GCD, here we have GCD, over the mass multiplied by time minus the velocity. Now, if I run this, I'll save it in some place. Better always to save it in the documents MATLAB folder. I'll say testing program 1. I get an error, and it says matrix dimensions must agree, cannot use the division. The m that we have defined is a vector, and you cannot divide by a vector like this. We use the dot with the division. We call this an element wise operation. Okay, so that it divides each thing by the values. Let's say I have vector mass. Let's say 1, 2, 3, 4, and I say 3 divided by mass. Then 3 divided by what value? It doesn't know. But when I say 3 dot divided by mass, this means it is an element wise operation. It means 3 divided by 1, 3 divided by 2, 3 divided by 3, 3 divided by 4, an element wise operation. So it does this operation on all the elements. We can use the dot with the division, we can use the dot with the multiplication, and we can use the dot with the power. So for example, I say m square, then this m to the power 2 is not going to work. I have to say m dot power 2. That means 1 square, 2 square, 3 square, 4 square. Okay, so this is called the dot operator in MATLAB. And similarly, now when I do this operation, I'll get a vector, and when I do this operator, I'll get a vector. So I cannot multiply vector with vector. I have to have an element wise operation between them. Let's say I have densities, mass over volume, and I have mass values, and I have the volume values. Let's say 3, 5, 7, 9, and I want to find the density for the different 4 different things that I have. So if I say density is mass over volume, doesn't work. I need to do an element wise operation. So I'll say element wise operation means for each corresponding value of mass divided by the corresponding value of the volume. So I'll get 1 over 3, 2 over 5, 3 over 7, 4 over 9. Same thing if I do multiplication, I say m with v with a dot multiplication, I'll get 1 multiplied by 3, 2 multiplied by 5, 3 multiplied by 7, 4 multiplied by 9. This we call it the element wise operations. So now it works. It gives me the mass as a vector with 100 values and f as a vector with 100 values. Plotting in MATLAB is very easy. It just say plot x and y, but have to be vectors and have to have the same length. I cannot plot a single variable. It must be a vector, and both the vectors should be of the same length. So here we have 1 by 100, 1 by 100, so we can plot them. First the x and then the y. The x is our independent variable, which is the mass, and our dependent variable y is the f. So plot m and f. It gives me a plot in a new window, and I can see the plot here. To see the lines here, I can say grid and it will add for me a grid to my graph, and I can see again now from here and copy the figure and I can paste it here. Doesn't paste here. Then the place where it crosses the the 0, that place I can call this as the root, and of course we can find the value of the root from here, somewhere near 140, as we said earlier. That's the answer, is somewhere near 140 kilogram. So this is the graphical approach where you plot your values of the independent variable and the function, and find where it crosses 0, and that you can read it from the graph to find the values. So this is the Excel and the MATLAB procedure for the graphical approach. Here you are given the same command almost, but is with a different range from 50 to 200, and gives you the same graph, and you can look at the root as the place where the function crosses the x-axis. So it says here that we can see it crosses between 140 150. So visual inspection of the plot says that we have an estimated value of 145 kilogram, or 140 as we have read it. It says we can determine the value of the function, comes out to be 0.0456, which is close to 0. So we say it is almost 145 kg or 140 kg, whatever you want to read it as. This is depends on your visual inspection of the plot. It will depend on the resolution of the plot for you to read it as you are going to read the value. Please try to use your mic to ask a question or say something. Going back to this is not very good. If you want to find the solution in MATLAB, we have to use the loop. No, I didn't use any loop. I have given you the graph here, and then you can see the solution from the plot. Says we can also check it by trying to find the value of the velocity at the mass that we have, and it comes out to be 36.0456, which is close to 36 meters per second. So we can say that we have a reasonable value for the mass that we have found from the graphical approach. A graphical approach is, it says, are of limited practical value. It means that practically they have a very limited benefit. You cannot really get much out of it because they are not very precise. You can see that we tried to read from Excel, we said it is 140 kg, then we tried to read from MATLAB, and it said that it is almost little bit more than 140. Then from the slides, it said that it's almost 145. So they are not very precise. The resolution depends exactly on how much work you are going to put into making your plot. So they are really not very useful. And of course, you are going to sometimes need these values for further calculations. So you cannot tell MATLAB to plot and then go and read the plot and find out where it is crossing the x-axis. So you cannot tell Excel to go and read the plot and find where it is crossing the axis. So you need maybe this value and start other calculations with it. So it's really not a very practical approach. However, we can still use these graphical methods to get rough estimates of the roots. So you can still use it to get some rough estimate that you can use it as a starting guess value. We said earlier that numerical methods are trial and error procedures. So you try with a guess, see whether it works. If it doesn't, then you go to another one. Now, if that didn't work, then you go to another value. So if you don't have a good starting point, then you are going to waste a lot of time trying to look for the values. So you can use the graphical approach to find for your good starting guess value, so that then you can use a numerical method and get your more accurate values for the true value by applying the numerical methods that you have. Graphical interpretations are also useful for understanding the behavior of the function, how the function is behaving. And we will see later how different numerical methods have some pitfalls, means failures, when some of the numerical methods are going to fail. So looking at the behavior of the function, we can see which numerical method is more suitable to be applied here. When we apply the graphical methods, then there are some things that we can infer from these graphs that we are going to plot. Now, if you have a plot like this, as we have in figure A, where the function sign is same on the interval where you are looking at. Let's say we said this was the 50 kg and this was the 1 or the 200 kg, whatever limit that we have taken, and we found that the function sign is same on both the limits. Then this means that there is no root in this interval. Why is that? Because we can see that it has not crossed the x-axis. So we don't have a root in this interval. If one of them has a negative value and the other has a positive value, or if it's the other case, you have positive on one side and negative on the other side, it means you have different signs. Then it means that you have one root in this interval. We could sometimes also have that we have the same sign, positive on both sides, and we think that we have a scenario like this where function values are same on both sides, so we don't have a root. But if you are going to plot, you might discover that you have actually two roots between these two values. So it does cross the x-axis, but it goes down and then crosses again. So you have two roots, not one root. Or you could have a scenario like this repeated, where you have a positive on one side and a negative on one side, but indeed you have three roots within this interval and not just one root. So graphical interpretation helps you to understand the behavior of the function and see exactly what method you are going to apply and or how you are going to work. So for example, in a case like this, it means the interval that you have selected is wrong. You are not going to find any root in this interval. Sometimes also you can find that you will have multiple roots where the function becomes tangential to the x-axis, where it just touches the axis and goes back. So it does touch the axis. So what we have is we have two roots at this value. Let's say where x plus 3 is equal to 0, so you'll get x squared plus 2 times 3 times 6. So the root of this will become x equal to 3 twice, or x equal to minus 3 twice. So you'll have the same root twice. We call this a multiple root. You could have a case like this where you have discontinuous functions. You have negative here, you have positive here, but in between you have a discontinuous function. Of course, when you have cases like this, then you need to have special strategies to find the roots. This we can understand once we do the graphical interpretations. When we plot the functions, we can come up with these conclusions and have a better idea about the behavior of the function. Now, we have different types of approaches that we apply, and these depend on the technique that you want to use for finding the roots. I give this example in the class, maybe not very practical now here in the online scenario. So let's say we have in the class students sitting in the class. Okay, that's much easy now. Now, while I'm moving around the class, let's say I forgot my marker with one of the students while explaining something to the student. And when I got back here now to write on the board, I find that I don't have my marker with me. Now, my problem is that I need to find the marker. Now, how do I find the marker? Of course, the easiest thing to do is I start from the student here, look at him if he has my marker, go to the next one, go to the next one, go to the next one, next, 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 until I find my marker. This is one approach. We call this the brute force approach, where you just take one value and you start looking for it. So I'll start from 50 kg and I'll see my function value. Is it 0? No. I make it 51 kg. Did I get 0? No. I'll make it 52 kg. And I continue, of course, until I reach 140 kg or 145, whatever you want to call it, until I find my function value becoming equal to 0. That, of course, is not a very good, not a very intelligent, not a very effective approach, because you are going to waste a lot of time. I could have forgotten the marker with the last student here, and I'll keep looking at all the students separately. Now, a better approach, of course, is that I try to recall to which student I went, and I only look for the marker for those students. So, for example, I might have gone to this student, and this student, and this student, and this student, and this student. So, instead of going to all the desks, I can just go to this student, and then this student, then this student, and find the marker. So I don't have to go to all the students. That's another approach that I can use. Of course, I can use a better approach. I can just ask the students to see who has the marker, and the student raises his hand that you forgot the marker here, and I directly go to this one person and take the marker. These different methods that we can apply. Similarly, we have different numerical methods that we apply to find roots for the problems, or any other numerical method that we are going to apply to any other type of problem. We have these different methods. They are differing on the technique that they apply, basically on how to change your guess values. We start with an initial guess value, or a starting guess value. Now, this did not match our criteria, did not give us the solution. What should be my new guess value now? The different methods that we have differ in how we are going to find the new guess value, how to change the guess value. Do I go from 50 to 51, or can I jump faster to reach the solution? How am I going to change my values? the different methods they are differing in these uh, techniques. The first method that we are going to use here now in this chapter, it's called the bracketing method or the bracketed methods. These work on knowing that we have an interval, and within this interval there is a root. So I plot my graph between two values. I call this the lower limit and the upper limit, and I know that there exists a root in this interval. How do I check for the root? I can make sure that I have a negative function value here and I have a positive function value here, or the other way around, that I have different sign on the functions. That means that I definitely have a root between them. It has indeed crossed the x-axis. So I can find a root using this bracketing technique. So this chapter is about bracketing methods. We'll look into these methods in the next lecture. I don't want to start now and we don't have much time left. I'll stop here, and if you have any questions, you can ask.